Okay, students, now let us look at this decomposition, and I think one of the main takeaways of this lecture has to be this decomposition, right? The fact that you have any block matrix, you can actually pre-multiply and post-multiply to get a matrix, a block diagonal matrix that involves Schur complements. Let's look at one direct immediate consequence of this decomposition, right? Now, what is special about this matrix and this matrix over here? It's very easy to see that this matrix is block triangular, no doubt, right? It's block triangular. In fact, it is block upper triangular. There's nothing in lower triangle. But because these matrices are identity matrices, it is also actually a triangular matrix, right? If you write it down, if you expand this block and write it in terms of the identity matrix 0 1 0, and if you imagine drawing a diagonal like this here, you see that all the entries below the diagonal are 0, right? So this is actually an upper triangular matrix, right? I could not have said that if this were like an arbitrary square matrix, right? Then below the diagonal you could also have some non-zero entries corresponding to whatever entries this matrix has. But this is identity, so below the diagonal it has all zeros, below the diagonal this also has all zeros. So this overall matrix is triangular. Similarly, this matrix is also triangular, right? So we readily know what the determinant of this matrix is, right? What is the determinant of this matrix? So determinant is 1. The determinant of this matrix is also 1. Okay? The determinant of both of these matrices is 1, and we know the determinant is multiplicative, right? So when you have a product of matrices, determinant is the product, right? So the determinant of the matrix M, so remember this is a matrix M, the determinant of the matrix M is the same as the determinant of M by D 0 0 0, this block diagonal matrix. Okay. Now what is the determinant of this block diagonal matrix, right? When you have a block diagonal matrix, when you take the determinant, so any block diagonal matrix for that matter, when you have P0 0 Q, right? So long as P and Q are square matrices, right? So P is square, Q is square, which is the setting anyway we assume for Schur complements. If P and Q are square matrices, then the determinant of this overall block matrix is just going to be determinant of P times determinant of Q. Okay, it's determinant of P times determinant of Q. This will follow just by applying the definition of the determinant and using induction if you want to use induction, right? So I'll leave for you to actually see how you can visualize this. But if you remember the definitions of the determinant we had in the first segment, one of the definitions was the definition based on permutations, right? You find the determinant by picking one entry exactly from each row and each column of the matrix. That's how you pick it, right? Now here, if I have to pick an entry from one row and one column, I cannot pick any of these entries, right? If I let's say from the first, so let's just categorize this. This is n rows, this is m rows, this is n columns, this is m columns, right? So from the first n rows, I cannot pick any of these entries, right? Because then the term product will be 0 anyway, right? So that means from the first n rows, I'm only forced to pick entries from the first n columns, okay? Which is precisely what you would have done if you were trying to find determinant of P, right? Similarly, from the next n rows, I can only pick entries from this portion, meaning from the last n columns, which is precisely again what you would have done when you have picked determinant of Q. Okay, so basically using that intuition, you can argue that the determinant of this overall matrix is determinant of P times determinant of Q. I'm leaving this proof aside because it digress a bit too much from the topic of this lecture, but nevertheless it is very easy to actually imagine, because after all we know the same thing happens when you take a diagonal matrix, right? So if P and Q are scalars, right, P0 0 Q, the determinant is simply PQ, right, the product of the diagonal matrix. Same thing is happening here when you have block diagonal matrices. Okay. So this determinant in turn, this determinant over here in turn is equal to det of M by D, that is the Schur complement of D times det of D. Okay, this leads to the first important and not so obvious result, is the determinant of M is equal to determinant of D times determinant of Schur complement of D. Now you see why the M by D notation was first introduced, because it's as if the D cancels here. It's as if the D cancels and you end up with M. It's as if that, right? That's why you write it as M by D. Of course, it's also going to be equal to determinant of A into determinant of M by A by a similar argument. Very similar argument will give you determinant of A into determinant of M. Okay. So this result actually, let's just expand this a bit, right? Let's take this one and expand it. So this is actually determinant of A times determinant of D minus C A inverse B, right? So this is what it is going to be. Now, if you had a 2 cross 2 matrix where the A, B, C, D were not matrices but the scalars, right? So small a, small b, small c, small d, just a 2 cross 2 matrix. What is the determinant here? AD minus BC, right? And if this with a bit of manipulation is trying to be too clever, you can write it as A times D minus C A inverse B, right? Is it? So you can write it. So this result over here can be seen as a generalization of this, right? When you have a 2 cross 2 matrix filled with scalars, this is the determinant. But when you have a 2 cross 2 matrix that's defined in terms of blocks, then this is the determinant formula for that. Okay, the direct generalization of the scalar case. Okay, just that here we have to be more careful because I have to take A common because A is invertible here, A is square and invertible, B and C may not be invertible, and I have to pay attention to the order here. It has to be C A inverse B, it cannot be B A inverse C because that doesn't even exist, right? Whereas here the order doesn't matter. Okay, fine. So this is basically the idea. Also of important thing to note here is that there are essentially both of these are correct. You can either write it as det A times this, or you can write it as det D times this. You can actually do both of them, right? And in general, whenever you see two ways of writing the same thing, it's usually indicative that something very miraculous can happen in that. For example, let me just try to construct this example. Consider the following block matrix. I. So let's say this is IN, okay, this is minus C, this is B, and this is IM, okay. So this is N cross N identity, this is M cross M identity, okay. So the matrix C here is N cross M, the matrix B here is M cross N. I'm just putting minus C as an example. You'll see why I'm putting minus C in a minute. Okay, minus is actually not very important there, right? So N cross, so this is the basic structure we've been looking at, but I'm assuming that this A and D are identities now. Okay, I'm just making the simple assumption that A and D are identities. Let's try to expand this determinant by applying the Schur complement. One advantage of assuming A and D are identities is that it's very easy to find the Schur complement, right? For example, if I want to find the Schur complement of A, I use this formula. If A is identity, then the inverse of identity is just identity, so I don't have to worry about what it is, right? So in fact, what will be the Schur complement of IN? What will be the Schur complement of IN, right? So to find the Schur complement of IN, N cross N identity, I'll just start opposite. IM minus B, IM minus B times IN inverse C. IN inverse is just IN, so you'll just minus, you'll have B times minus C. Okay, so that's just going to give you plus BC. Okay, that's what M by IN is. Let's compute the Schur complement of IM, right? To find the Schur complement of IM, I'll start with IN and run clockwise like this, right? So IN minus C times IM inverse B, okay? So that's going to be IN plus CB, okay? Change in order, okay? Okay, fantastic. So now let us try to apply these equations. So what is the determinant of M here? The determinant of M will be this determinant, right? This determinant is equal to det D. Now D is just identity, so this is 1 times det M by D. Okay, so this is just going to be equal to det of IN plus CB. Okay, now if you write the second term here, you'll get det A. Again, A is just IN, so this is 1 det M by A. M by A is equal to this one, IM plus BC. Okay. This gives you a very powerful result. It tells you the determinant of identity plus a product of two matrices is the same as determinant of identity plus the reverse product. Okay, it's very interesting because B and C, remember here, don't have to be square matrices, right? This is n cross m in fact. This is m cross n. Of course, B and C must be such that BC and CB are readily computable. Meaning that, if B is m cross n as here, C must be n cross n. So that this product makes sense, and similarly, this product also must make sense. Okay. So important thing to see here is that this matrix is of a different size, right? This matrix here is of size m cross n. Okay, indeed, this is the m cross m identity. This matrix here is of size n cross n. But you are saying that these two matrices must have the same determinant, right? These two matrices of vastly different sizes must have the same determinant. This identity is often, you use it often, for example, in finding maximum likelihood estimates when dealing with multivariate Gaussian variables, Gaussian random vectors, for example, right? This has a name, and you'll see Sylvester's name appear many times in this in the next lecture. So Sylvester's determinant identity. It goes by some other names as well, so it's not very clear. I don't think this is a very standard name for it, but nevertheless, I think it's fairly common enough. People use this name. Okay, the Sylvester's determinant identity says that for example, if you have, let's say, a vector x, right, and if you have x transpose. By the way, what's the determinant of x transpose? Anybody know what's the determinant of x transpose? X here is an n cross 1 vector. X transpose is the outer product of x. What's the determinant of x transpose? Well, can I write it as determinant of x into determinant of x transpose? Somebody point out the obvious mistake in this. Well, x is a vector, right? X is not square. It doesn't have a determinant, right? So you cannot actually write it like this. Okay, you can use the formula det AB equal to det A into det B only when A and B are both square. Correct? That's when determinant can be computed. Otherwise, you can't find the determinant, right? This determinant is going to be 0. I'm going to leave you to verify why that is. Exercise. Any doubts, please ask. Okay. Now, what is determinant of identity plus XX transpose? Okay, so XX transpose is the outer product. It's an n cross n matrix, right? So here it's an n cross n identity that I'm adding. The determinant of identity plus XX transpose. So this determinant, well, by the Sylvester's determinant identity, this is the same as det of x transpose x. I'll simply swap the order here. XX transpose, I'll swap it to x transpose x, right? Now x transpose x is just 1 cross 1, so I need to just put a 1 cross 1 identity here, right? Which is just 1. 1 plus x transpose x, which is just 1 plus 2 norm of x whole square. So that's the determinant of this matrix, right? Instead of applying the definition and doing all those things, you can readily say that by the Sylvester's determinant identity, this determinant is 1 plus norm of x whole square, right? All I did is simply swap the order of matrices here, right? Because if you swap, the determinant doesn't change when you have the identity up front here. Okay, so this is one immediate direct consequence of the matrix decomposition property that we are discussing here. Let me just cut it and paste it below also so that I can use it instead of writing the whole thing again. Right. Good. So we have this matrix here. So let me write down the other part is missing here. Is equal to m by d 0 0 d. Okay. So the main advantage here is we were able to diagonalize this block matrix, and that's what gave us the determinant identity, is it not? Right? You can get a bunch of other things just by diagonalizing, right? For example, these two matrices over here are invertible matrices, is it not? Right? These two matrices over here are invertible matrices. So what can you say about, let's say, the rank of M? This matrix is M here, right? So let's call this matrix as S and this matrix as T. These two matrices are invertible matrices. So rank of M is going to be equal to the rank of the diagonalized version, M by D 0 0 D. Correct? Because when you have invertible matrices multiplying either in the front or the back, rank doesn't change, right? We discussed this in the very first segment, right? So these two are invertible. That's the key here. They're invertible because they are triangular matrices with ones on the diagonal. Okay, they are invertible. Okay, so rank M is equal to the rank. So basically the rank of the matrix is the same as the rank of the diagonal. Now what is the rank of this one? Right? So whenever you have, let's say, a block diagonal matrix like this, right, 0 q, what do you think is the rank of this? Right? So basically you have to look at how many linearly independent columns are there, right? If you have to go by that definition, you look at how many linearly independent columns are there, correct? Now any column in this matrix is going to be linearly independent of any column from here, okay, because they have zeros in non-overlapping positions, you see, right? So if I construct a linear combination of columns, right, if I construct a linear combination of columns, then what you would get is simply going to be that any column here is going to be linearly independent of any column here, right? So all I can simply do is pick a linearly independent set of columns from here and a linearly independent set of columns from here and put them together. That's going to give me a basis of the overall column space. Okay, in other words, take linearly independent columns from this portion and linearly independent columns from this portion and put them together, right? So this is just going to be the sum of the ranks. So it's going to be rank of the Schur complement plus rank of T. Okay, rank of the Schur complement plus rank of T, right? So this is happening precisely because of that. There's another way you can actually see this, right? You can also try to find a vector in the null space of this and use the rank nullity theorem. That also will give you a very similar result, right? For example, what is any vector in the null space of this matrix, right? So you can do P0 0 Q times x1 x2 equal to 0, right? That gives you Px1 equal to 0 and Qx2 equal to 0. That means what? X1 needs to be in the null space of P and x2 needs to be in the null space of Q. Okay. So to construct any vector in the null space of this big block matrix, I need to pick the first portion to be from the null space of P, second portion to be from the null space of Q. Okay. So what is the overall dimension of the null space? It's going to be the sum of the dimensions of these two spaces. Correct? So the overall nullity is going to be the sum of the nullity of P and nullity of Q. Then you apply rank nullity theorem, which will tell you that the overall rank is the sum of the ranks of P and ranks of Q. Okay. So rank of M is equal to rank of Schur complement, and of course you can also write it as rank of A plus rank of Schur complement of A. Okay. So determinants multiply, ranks add, for the matrix and its Schur complement. There's also something even more interesting that is a bit of niche things. I don't know if it will be useful to you guys, but I'll just mention it anyway, right? So suppose that the matrix M happens to be symmetrical. Okay, this is the scenario we discussed in the very beginning, right? The matrix M happens to be symmetric. Then C is equal to B transpose, right? And C is equal to B transpose, and A and D are both going to be symmetric. Okay. Then let us rewrite this decomposition under those constraints, right? So you'll get something like IN minus BD inverse 0 IN times A, B, B transpose D multiplied with, well, what will happen here, right? So IN 0, you have minus D inverse C here, okay? I'll write it as minus D inverse B transpose, okay? So if I call this overall thing as S, right, then this overall thing becomes S transpose. Okay, this is equal to M by D 0 0 D. Okay, this overall thing you call as S, this overall thing becomes, sorry, if you call this block matrix as S, this is simply S transpose, right? You can see that because if you take the transpose of this quantity will end up here, which is precisely what happened here, and then you will get D inverse transpose B transpose, right? But D is symmetric because the overall thing is symmetric, D is also symmetric. So minus D inverse B transpose, this is what you will get. Okay, S and S transpose. Now there is a very interesting result, a parallel different result, which I'll just write it down anyway. So theorem, it's called Sylvester's law of inertia. I didn't mention it earlier. Ideally, this goes into the really min-max theorem portion, right? Lecture 3. I didn't mention it because lecture 3 already was getting bloated with a lot of advanced topics. This is also fairly advanced in the sense I don't know if you will ever need it, but let me just mention it for what it's worth. Right? Sylvester's law of inertia actually says that when you have something like this, so when you have a matrix M and when you have S and S transpose multiplying, this S needs to be invertible matrix. It doesn't have to be orthogonal. Right? It can be invertible. Any invertible matrix like we have here, right? We have an invertible matrix multiplying here, right? Then this new matrix, right, is also symmetric, right? M is a matrix symmetric to start with. This overall matrix is also symmetric. You can easily check that by taking the transpose, right? It is symmetric, it has eigenvalues and so on and so forth, right? So what Sylvester's law of inertia says is that if you look at this matrix and let's say you look at how many positive eigenvalues it has, okay? So let's say I take all its eigenvalues and I, sort them like we have been doing before. Where is the undo? Okay. I sort them, right? So basically lambda, first eigenvalue, second eigenvalue, third eigenvalue, so on. And let's say this is my origin. Okay, this is origin. So I look at all the negative eigenvalues, okay, all the positive eigenvalues, and there will be some zero eigenvalues. There could be many, zero eigenvalues. Right? Counting with repetition as usual whenever we're dealing with symmetric matrices, right? So negative eigenvalues, positive eigenvalues, and zero eigenvalues. Okay? Sylvester's law of inertia says that when you start with a matrix M and when you apply S and S transpose, pre-multiply with S and post-multiply with S transpose, that does not change the number of negative eigenvalues, number of positive eigenvalues, and number of zero eigenvalues. It may actually reshuffle the eigenvalues within this bracket, meaning that the eigenvalues may become more negative, they may become less negative, but if they are negative, they'll stay negative, right? If the eigenvalues of M to start with are positive, even after doing this SMS transpose, the eigenvalues will stay. However many eigenvalues were positive earlier, will stay positive now. Okay? So for example, if M was let's say a 10 cross 10 matrix with 5 negative eigenvalues, 2 positive eigenvalues, and 3 zero eigenvalues. Okay, then SMS transpose will also have the same decomposition: 5 negative, 2 positive, 3 zero. It may not have exactly the same eigenvalues, but the signs will stay the same. That's why it's called inertia, in the sense that you're doing something to it, still some of these things are not changing, right? So that's the main idea. The eigenvalues could actually change. In fact, you guys can possibly see this, that if S is orthogonal, then eigenvalues also don't change. Okay. Eigenvalues also stay the same. Why is that? Can somebody very quickly, I think most of you might know this, right? Because you can easily look at this by constructing the characteristic polynomial, right? So you have det of, remember, lambda I minus a. It is the characteristic polynomial where a is the matrix. Now here this matrix is S M S transpose. So just by a bit of trickery, you can write your identity as S transpose S, or whatever, SS transpose. Let's write our identity as SS transpose minus SMS transpose. And by taking S and S transpose common, you will get determinant of S times determinant of lambda I minus M times determinant of S transpose, right? Now determinant of S times determinant of S transpose is 1, okay, because S is orthogonal, right? So you can simply erase these two terms. So what you are saying is that the characteristic polynomials are the same and hence the eigenvalues are the same, okay? So if S is orthogonal, eigenvalues also are the same. What Sylvester's law of inertia is saying is that even if S is not orthogonal, so as long as it's invertible, right, and you have S and S transpose outside, the eigenvalues will not change their the overall decomposition of how many positive, negative and zero eigenvalues are there will stay the same. That will not change. Okay. This is actually a very direct consequence of the min-max theorem. So I leave it to as an exercise. Those of you who are interested in looking at this can try to see how to do it. But I'm going to skip the proof here, right? This is just something interesting to know. As I said, at least I have not seen it find use in at least a lot of core engineering problems, unlike the other topics that we are covering. Okay. So if you apply Sylvester's law of inertia to this, right, what does this actually say, right? It says that, the number of positive, negative and zero eigenvalues of this matrix will be the same as the number of positive, negative, zero eigenvalues of this block diagonal matrix. Okay. Now let us look at the block diagonal matrix. What are the eigenvalues of a matrix like this, P0, 0, Q? So let's say that P and Q are symmetric. What are the eigenvalues of this matrix? Right? There are many ways to see this. You can directly see it from the definition. Right? So in fact, if lambda 1, lambda 2 up to lambda n are eigenvalues of P, and mu1, mu2, so on up to mu n are eigenvalues of Q, mu m. Okay, this is n cross n and this is n cross n, right? Then the overall eigenvalues of m will be a combination. So it will be lambda 1, lambda 2, lambda n and mu1, mu2 to mu n. Okay, so this matrix will have n plus m eigenvalues, and there will just be a combination of the eigenvalues of P and the eigenvalues of Q, right? You can see that many ways. Let me do the characteristic polynomial root, and I'll leave the other root as exercise to you. You can find the characteristic polynomial of this block matrix, right? So lambda I minus m. So when you consider det of lambda I minus m, that's going to be determinant of lambda I minus p, 0, lambda I minus q, right? Now by the formula that we just discussed, when you have a block diagonal matrix, the determinant multiplies. So you get determinant of lambda I minus p times determinant of lambda I minus q. This is what you will get, correct? So you can see that the characteristic polynomial of the block diagonal matrix is a product of the characteristic polynomials. That means the roots of this are going to be a union of the roots of these two. You take any root of this, okay? You take the roots of this and the roots of this. You take the union of those two sets, that will give you the roots of this matrix. Okay, that's how you get it. The other way of proving this is to simply use the definition, and I'll leave that as an exercise to you. Okay, in fact, I'll ask you a slightly more complicated question. What are the eigenvalues and eigenvectors of P00Q in terms of eigenvalues and eigenvectors of P and Q? Okay, so leave this as an exercise. Please do work on these problems. It's very easy for me to directly lift these problems and put in the exam, just to make sure that everybody has seen the lectures, right? Okay, so that's the main idea. So what I'm trying to say is that there are two levels of argument here. I'm trying to say that by the Sylvester's law of inertia, whatever negative, the number of negative eigenvalues of this is equal to the number of negative eigenvalues of this, right? And the number of negative eigenvalues of this matrix is equal to the number of negative eigenvalues of this plus the number of negative eigenvalues of this. Okay, so let us say if nx denotes the number of negative eigenvalues of x. Okay, I'm just introducing a new notation. Sometimes this is called the inertia of a matrix. The inertia of a matrix. Okay, then what you are saying is that nm, the number of negative eigenvalues of m, is the same as the number of negative eigenvalues in A plus the number of negative eigenvalues in the Schur complement of A. Of course, you can write it also as number of negative values in D, negative eigenvalues in D plus the number of negative eigenvalues in the Schur complement of D. Okay, this is called the Ainsworth inertia additivity. Okay. Of course, there's nothing special about negative here. You can also write the same thing for positive eigenvalues. The number of positive eigenvalues of m is the number of positive eigenvalues of A plus the number of positive eigenvalues of the Schur complement of A. You can also write it for the number of zero eigenvalues, right? The number of zero eigenvalues of m is equal to number of zero eigenvalues of A plus the number of zero eigenvalues of m by A.